This is Dr. Bess Miller, and I'm here with Dr. Chin-Yih Ou. Today's date is November 17th, 2017, and we are in Atlanta, Georgia at the Centers for Disease Control and Prevention. I am interviewing Dr. Ou as part of the Oral History Project, The Early Years of AIDS, CDC's response to a historic epidemic. We are here to discuss your experience during the early years of CDC's work on AIDS, the acquired immunodeficiency syndrome. Dr. Ou, do I have your permission to interview you and to record this interview?
Sure, you.
Dr. Ou, you have had a distinguished career in HIV laboratory science. When you first came to CDC in 1986, you took the lead in applying the newly emerging methodology of polymerase chain reaction, or PCR, to the diagnosis of HIV. Really a revolutionary event. You went on to work on this methodology to allow for the diagnosis of HIV in infants. Your work in the use of DNA sequencing to look at genetic diversity of HIV proved invaluable in identifying HIV transmission in the so-called Florida dental investigation. Your work has been published in Science and the New England Journal of Medicine, among others, and you have been awarded the highest science award at CDC, the Charles C. Shepard Science Award. Thank you for agreeing to do this interview.
Thank you for having me.
Let's begin with your background. Would you tell me about where you grew up in your early family life?
I grew up in Taiwan. My parents were actually from mainland China. They fled away from the communists taking over of China to Taiwan with 4 children, and actually I was the 5th. I was born in Taiwan and lived my life mostly in Taiwan until I came to the United States.
So, did you have scientists in your family? Do you remember what inspired you in terms of what you wanted to do in life?
Yes, actually my parents they were teachers. They were teachers in Chinese literature and things like that, and they taught in high school. And our 6 siblings, 2 of them, 3 of them, including myself, were scientists. And they actually, most of our siblings were educated in the United States for higher education. They got their PhDs here. And one of my sisters actually got a degree in literature, and she taught Russian language in Taiwan. And the last younger sister, just like my parents, she taught Chinese in high school.
So where did you end up going to college?
I studied medical technology in Taiwan National University, and later on I moved on to study microbiology and have a master's degree there, also in National Taiwan University. And we have to have a mandatory Army training for 2 years. So I was in Taiwanese Army for 2 years before going back to graduate school. And actually between those 2, I also work as a laboratory director in a small clinic, hospital in Taiwan.
So what brought you to the United States?
I went to Tennessee, the Oak Ridge National Laboratory, to study molecular biology back in 1977. And I actually stayed there until 1982, and then 2 years postdoc to 1984.
Wow, so that was a big jump. What inspired you to do that?
As I said, I actually started my career as a laboratory scientist since I finished my Army duty. But I found that it was kind of boring. I don't want to go in and day out and just doing the clinical laboratory work. So I decided to go back to graduate school.
And the U.S. was the place to do that?
Well, most people actually at that time came to U.S. for higher education, for their PhD and so forth. And as I said, 4 of our siblings came to the United States, and 1 went over to Europe. So we were all over the place.
So at Oak Ridge for your PhD, what was your area of concentration? What was exciting to you, or what was in vogue that you ended up studying there?
Well, I was working on murine leukemia virus, and this is one of the retroviruses. At that time, it was interesting to me because I just wanted to do something new. I came to the graduate school. In the beginning, I thought I wanted to do enzymology, but after 3 months trial in a enzymology laboratory, I found that is way too difficult for me. So I want to move into something different. Virology and molecular biology at that time was just starting. And I have to learn everything myself because things were new. And not that many people knows how to do it. So I have to learn everything, looking at the literature, the newly published literature, and try it myself. And that actually helped me a lot later on in my CDC career because I was doing retrovirology, and HIV is one of the retroviruses, and I learned all the basic techniques from cloning, sequencing, and everything. So I can quickly apply whatever I learned to HIV. And so the timing was just perfect.
Mm. So you moved to CDC in October of '86 to work in the Laboratory Investigations Branch in the Division of HIV/AIDS. And first off, you were tasked to establish a new microbiology, molecular biology lab, and you eventually became chief. What was involved in setting up this molecular biology lab?
Interesting to mention that. Actually, before I came to CDC, I was thinking to go back to Taiwan because at that point I kind of accepted a position there. I went through an interview, and then CDC job came up, and I happened to see that advertisement in Science, and my wife says, why don't you apply for it? And she helped me actually send out quite a few applications besides CDC. And I got only 2 replies. CDC position was one of them. And I came over to talk to Dr. Sharkiman, who actually came a year before me, and he was trying to also set up a new direction of the research or the application of work here in his new capacity. And we talked, and he wanted me to kind of look into the HIV genetic information in patients. And actually he wanted me to use a new technology that was at that time published by NIAID scientists. And we were about to go for that. But right before I came to CDC to work, I happened to read a couple papers. One of them were just published about the same time, and I was astonished by the new technology, PCR. And I thought at that point, have I had this technology available to me, I could have cut down my PhD research by at least 2 or 3 years because it was so fantastic. And with my background in clinical microbiology, I can see that technique can be used right into HIV field to diagnose HIV. And Jerry was very nice. He gave me a new laboratory, and actually this laboratory has nothing in it at that point. So I have to order the chairs, the chemicals, everything from the scratch. And it was a very fantastic experience for me. And in the beginning, as I said, we decided to go for the technique that was just published by NIAID people.
What technique was that?
This is a technique for in situ hybridization, very similar to PCR, but it is looking into these cells to see whether they harbors HIV sequences, RNA, and that kind of thing. And then you combine with other immunocytology type of technique also to identify what kind of cells that they are, like T4 cells or macrophages. But to me, I thought it was a very labor-intensive technique, and you have to see the cell morphology. It also happened that they told us that I have to go to their laboratory for 6 months to learn this thing. And so we decided that was just way too long. And so Jerry and I decided that, sure, we just move into PCR right away.
So we're talking about trying to do a more efficient way of diagnosing HIV infection. What was the sort of the state of the art at that time before using PCR or moving into the direction that NIAID was moving?
Well, certainly at that point, the way of diagnosing HIV infection was using antibody. If you have antibody to HIV, that means you're infected by the virus. But there are many other occasions. Antibody presence doesn't mean that there's infection. For instance, in infants, maternal antibody persists at least 9 to 18 months in many infants, so you cannot do that. And if you want to see the real presence of HIV, it would be done through cultural technique. And culturing viruses takes a long time. At that point, you need to have HIV culture laboratories, and then about 4 weeks before to see the virus replication using the reverse transcriptase activity to judge, and that's just way too difficult. Mm-hmm. And antigen detection is very insensitive. And that's why I was thinking probably PCR technology is the way to go, because you can amplify HIV sequences millions of times.
Fabulous.
Right.
Also, as you're coming in and you're setting up this new laboratory, what are your recollections of the role of the lab at CDC at that time? Was it a reference lab, a research lab? Were you paving new ground and moving into this lab?
There were a lot of activity in terms of research, sort of NIH type of operation, and I think that was the reason Dr. Schackman wants me to kind of move away from that kind of activity to do something that would be useful for CDC. And I think that was a tremendous decision. It is very hard to get a laboratory person to move away from basic research. At that point.
Did you struggle with that, or did you feel like?
Because as I said, I have medical microbiology background, so I understand why you need this kind of thing. So no, there's no hesitation in my part at all. The timing was just right.
So can you tell us a little bit more then about establishing this PCR technology in the lab? And it sounds like you had some management responsibilities. Who did you recruit to get this up and running, and what was involved in getting up to speed on being able to use PCR technology?
Well, in the beginning, it was all by myself because I was the only person. And there's another person who came in CDC with me and becomes my old friend, Clyde Hart, Dr. Hart, with me together. And I was trying to put PCR to work. And it's not that difficult, I actually get it to work in a couple of weeks. Once I, decided to get onto it, I have to get primers and things like that. I ordered commercially. At that point, there wasn't the core facility in CDC yet, so we ordered primers outside, and I put things together, and in 2 weeks, I started to see the beautiful results. And at this point, we have to use culture specimens derived from HIV patients, and Dr. Paul Fiorino, who was in charge of the culture laboratory, provided me all those materials. And this is a great point that, when I got this thing to work, it's not just myself. It's also my colleagues in CDC, and great decision from Jerry Schackman, who worked with me and provide me everything. So I began with a one single person operation sort of, but quickly when I get it to work, he would give me technical supports. And at that point, the very first two persons working with me were Sheila Mitchell and Jennifer Moore, and they were great helping me to get things running. Because in the beginning, think about back in the old days, we didn't have a PCR machine. There weren't commercial PCR machine at all, and everything had to do by hand. And I have to have two heat blocks, one heat block to denature the DNA, the other one for DNA polymerase, to start the chain reaction, and then also there weren't the heat stable enzyme, DNA polymerase. So every single step, I had to open up tubes, add the enzyme in, close it, spin it, and then heat it up, doing the DNA synthesis, and then open it up again, add a new enzyme, and so forth. And so when I run 35 cycles, this is a tedious approach. And I developed sort of a carpal tunnel syndrome very quickly. And I got sore hand every day.
From doing
home.
what?
From doing just open tubes, add things, close tubes, snap it, put it into refrigerator, put into a centrifuge to spin, make sure everything is down there, and start the process again. And you have to do this 35 times. And consider if you have 20 samples, how many times you have to do this.
So now, did you learn this from who had been sort of experimenting with this technology? Did you go there?
No, we just read from the publications. There's nobody to learn from. You just look into the publications and start from there. And you just need to try a few times. And as I said, I have a basic training on DNA synthesis before when I was in graduate school, and I know how to do DNA labeling and things like that with P32, because we had to do southern blot, and all those things. And in the beginning, we used culture cells, and they actually will produce, there are tons of DNA HIV copies in there, and so it's not that difficult to get them to work. But once you move into patient specimens, is another story. There are tons of human DNA in the background.
So when did you begin to do that? And what did you first, once you were moving past Dr. Fiorino's culture specimens, what did you start with in terms of trying to look at patients' specimens, blood, I assume?
Well, see, yes, and that's our goal. Our goal is not just doing a PCR using culture cells. We wanted to demonstrate that we can get this thing to work in the peripheral blood drawn from patients. And the beautiful thing also is that in CDC we have those specimens archived away, and so these specimens are in our serum bank or sample bank, and Paul got them, part of them, to do the culture, but the original samples saved there, so we can go back to those original samples and to make comparisons.
And these samples would be from various epidemiologic studies. Where were these samples drawn from that were archived at CDC?
Later on, in the beginning, yes, there are all different kind of specimens drawn for our epi studies. So they are well kept. And later on, for all the other studies, specific studies, there are specific cohorts. They are available to me. And so it's very convenient. Once the laboratory shows that this thing will work, then we work with our epi people together and get things done quickly. And this is the great thing about CDC. I don't need to go out and look for them or to start a new project to collect specimens, because sometimes it takes a few years just to collect those sequential or prospective samples. And for CDC, we just go back to our serum bank or specimen bank to get them.
So I'm aware that that there were a number of articles that you published on this, one of the first in Science, is that right, using this technology?
Mm-hmm.
And then it became apparent that it could be useful for the diagnosis of HIV in infants. Can you tell us a little bit, you mentioned it before, what was the problem in diagnosing HIV in infants? And now we're into 1989, 1990, and quite a few cases in infants and young children.
And yes, this is a very interesting, important question. Infants born to HIV seropositive mothers will carry mother's antibodies, and the half-life for antibody normally is about somewhere around, I think, 23 days. And so the maternal antibody has to decay before you can say, oh, this infant is infected or no. If they are not infected, the maternal antibody will decrease and disappear. If they are infected, then they will produce their own antibodies. And you can see the persistence of antibodies. Because at the end is the infant's antibody. In the beginning is the maternal antibody in the infants. And so if you want to treat the patients, infected patients early, you need to know they are HIV infected or not early. And maternal antibody is not the way to go. Then detection of viral antigens or viral nucleic acids by PCR appears to be the way to go. And so once we demonstrated that PCR can detect HIV directly from adults, we move right into patients, to infants. And I remember this particular meeting that Jerry Schacherman and I, with Harold Jeffrey and Martha Rogers, we sit in the small room in the back of Building 6 to talk about this. Basically the lab people say, hey, now we have this new technology. Now we can solve the problem for infants. And Martha was in charge of a study where the major sources of HIV infected infant specimens were collected from New York. And so this is a beautiful combination of a new laboratory technique to solve the problems we are waiting to be solved for quite a few years.
So, what was used at the time to try and diagnose the actual viral particles in infants? Was that nucleic acid?
That they weren't. That you have to wait. Even very late. Even in the last few years, in the 2000s, in Africa, most of the infants still diagnosed by antibody tests. But as I said, you have to wait. A few months, 9 months, or even longer. In the HIV, the WHO recommendation actually is 12 months to 18 months later. You have to see the disappearance or the persistence of HIV antibody in uninfected and infected infants respectively.
So you couldn't use culture then? Is it that
You can use culture, but it just takes a long time. There you need a culture laboratory, which is expensive, and it takes somewhere around 4 weeks or longer to do. And this kind of operation is impossible in resource-poor countries, like in Africa.
Yeah.
Yes.
So, did you use blood directly? There was a dried blood spot methodology?
No, at that point, we didn't use dry blood spots. As I mentioned to you earlier, the Martha Rogers, who is in charge of the New York studies, she had the specimens from infants stored.
Okay.
So we went right into it. And that's why it makes our speed very fast.
So how long would it take to do that procedure given the blood specimens?
Well, the testing itself at that point was somewhere around 2 to 3 days compared to the 4 weeks of culture. But today, this thing can take only a few hours with the newer technology. And you mentioned dry blood spots, that it provides a means to quickly get the specimen from infants' fingers or toes, and then ship to the central laboratory for testing.
So can you tell us how that works, that you actually use a type of paper and touch the blood spot to the paper? And
Yes.
Was that used for other things, or is that part of the...
That's the so-called PKU studies back in early days for the U.S. And even today, DBS is still used for a lot of genetic diseases. Yes, and so you collect the blood there. And HIV genetic information is very stable once the spot is dried.
Wow.
Yes, and can be stored actually for years. We actually, back in the old days, back in the early 90s or late 80s, we received specimens when we were testing dry blood spots from Africa. And some of the samples received from our laboratory, we look at them, hey, come on, you have mold growing, you didn't dry your spot completely. And so things start to grow. And even there, we can retrieve nucleic acids for testing. And for sure, these days, there's a SOP, the standard operational procedures that require people to dry the spots, put it under an oven or dry at room temperature, and make sure they are dry before you ship. And dry blood spot today even being used for viral load determination. So it's quite an interesting substrate to, collect patient specimens for a lot of things.
So I guess the heat does not kill the HIV virus.
Actually, it kills. But on the other hand, the virus will not be viable anymore, but their nucleic acids are there, and the nucleic acids are the things we are looking for. And even if there's a degradation, breaking down of DNA, it is fine because we are only detecting a small portion of it.
Wow, that must have been really exciting.
Yes.
And did you publish these? I know you did, but do you remember some of the journals you published these articles in?
In terms of DBS or?
In terms of using PCR to diagnose in infants.
Oh, yes, and this is the paper written by Martha Rogers, myself, and a whole bunch of other people from New York, and it was published in New England Journal of Medicine. So it's a very, very prestigious, journal, and it is one of the two very first publication in the use of PCR for infant diagnosis, and it's still being done today.
So you sort of reached fame and fortune early in your career at CDC. What was that like? Was it stressful? Was it fun?
Well, at that point, actually, it wasn't stressful until a little bit later stage for other investigations. And there, I think it was a lot of fun because I felt like that I'm a little kid came into a candy bar store, and I can reach out for anything that I want, and we are experimenting something that other people never done before. And also, I have to say, I forgot to mention to you earlier that we got a great help from the company who invented PCR. I happened to read the publications they published in 85 and 86 when I was coming to CDC to work, so I know they are having that. But once we start our work, we realize that, doing the way that we do manually is impossible, and it's not good for clinical diagnostic work because contamination can become a big problem because you are amplifying a whole bunch of viral sequences, and those sequences will later on will become a contaminant for the new patient specimens. So I have to keep the laboratory clean. I mop my own laboratory. I clean the handles and everywhere that I can think of. I will come in on weekends to clean the laboratory myself because I don't want other people to mop my floor. So I was very careful. And then we reach out for CITES for help to see whether they have any new technology available in addition to their publications. And they were very helpful. John Slinsky and Sherry Quat helped me a whole bunch. So actually, in terms of the PCR paper, the real final test on patient specimens, I actually carried them to CITES to double check everything.
So this was for the science paper,
yes.
The original?
And then the rest were done here in CDC. But on the other hand, as you mentioned, this is new. And we laboratory people always try to do new things. And the way that we were doing, we had to use P32 to do detection.
Now, explain what the implications of that are.
Well, too tedious, and it's radioactivity. And then we have to expose the film in order to see the HIV sequences that we amplified. And it takes 2 to 3 more hours for film exposure. And to us, that is even too long. We want to cut it down even further. And so at that point, I also reach out to another company, GenProbe, in San Diego. So I went over there to talk to them to see what kind of new technology they might have. And actually I knew. So I went to talk to them. And they were very helpful too.
What was the technology?
It is acridinium labeled oligonucleotides instead of P32 label. So now I move from radioactivity to a non-radioactivity probe, and also it is done in a way that the machine would do the detection for us.
Okay.
But at that point, the machine is this big, huge machine. But people are very nice, you know. It is important for us, people working in CDC, to reach out to. We don't need to rely on our own technology because in many places we don't have. And the company out there, actually, they have new technology. And they love to work with us, people in CDC. And we come together and discuss the need of ours and their technology, and we sign, you know, collaboration agreements, and we put things together, and it works just beautifully. And that's something I really learned to best use our CDC's, name to help us.
It sounds like some of these things might have cost a little bit of money. Did you have the resources to travel and to purchase equipment? What was that like? We're talking about the early 90s, the late 80s.
I think at that point, at least, even now, I think, compared to quite a lot of operations that I know in CDC, the AIDS program had really plentiful resources and money. And I was lucky. Our organization has enough money, and we can travel, as you said, and talk to the people, and to put things together. I was really lucky.
Was there competition in this arena with NIH and some of their research?
For sure. And actually, in the beginning, as I mentioned to you early on, that I always wanted to get PCR to work, even before the day that I come to CDC. And in the beginning, Jerry Schackman thought in vitro hybridization might be the way to help us out. But then I was thinking, maybe PCR is the way to go, because I just happened to see the new publication then. And so, and at that point I really worried that somebody, as you said, in NIH or in Paris, those French people who cultured the first HIV virus, they would have known this. It doesn't take me, somebody, just have a fresh PhD or postdoc work to come up with this idea. And so in the beginning, I was really worrying, and I have an empty laboratory that I began with, and I said, well, whenever the Science or Nature journal came out weekly, I would open it up and see where anybody publish it, So the pressure then is that I really worry somebody else did. But evidently, and this may be for the younger generation, younger people, younger scientists, laboratory scientists, to see this as well. If you believe something, go ahead and do it. If you worry about it, that doesn't help you. And it happened that those big scientists in NIH or in France, they have big projects ongoing. They have to worry about their project. They didn't happen to see the paper. Not that we are brighter. It's just that, I happen to see the paper.
You're faster. Give yourself some credit.
Yeah, and we got help from people in Cedars. who invented PCR machine? Kerry Mullins got a Nobel Prize on that, in 1993, a few years later. So yes, I was very lucky. Timing was just great. But I take the credit that I didn't waste time. So the day that we submit our paper to Science and got accepted, I was so happy,
It sounds like Dr. Schocketman gave you a lot of support as well.
Oh, that is for sure.
And the Office of the Director.
Yes. And this is one thing I really am very grateful. I'm a foreigner. At that point, I wasn't even a U.S. citizen. I'm working in this organization, and this is a huge place. I was a small potato, and I cannot speak English well then, not now even. And they gave me all the supports that I need. And when they saw that this thing is working, they throw me everything, people, help, hands, and I was very grateful for that.
Moving on, you ended up doing some work in looking at the genetic diversity of HIV. Tell us a little bit of what's involved in that, and why was that important?
Well, first, my PhD dissertation actually was on the genetic organization of murine retroviruses in mouse genome. So I was doing the sequencing, that kind of thing. So moving from that background to HIV wasn't any difficult for me. And HIV is known to mutate because its reverse transcriptase wasn't perfect. It makes a lot of errors. And so when HIV infected in one person, if even there's only one originated from a founder or one single virus, eventually it is going to create a whole bunch of siblings, quasi-species. And the degree of diversity within one person change over time, gets greater and greater each year. And if one person infect or transmit the virus to a second person, it is going to do the same process, but will be similar to mine if I transmit a virus to that person, and so forth. So this becomes an interesting character for us to look at it, to decide whether one person transmit a virus to a second person. And I need to bring up Dr. Horsberg here. Bob Horsberg working with me very closely. So one day I was trying to test this idea, and he gave me 20-some specimens from his Boston partner cohort collection. And he told me that, okay, I have one source patient, and then here I gave you a whole bunch of 20-some people, and one of them would be his partner. We know that he transmitted the virus to him. I said, this is great. So once I got the result done, I called Bob. I said, Bob, you told me that there's one person infected another person among these 20-some people. But I said, that's not what I see. I said, I saw two. I saw two persons. So I worry, why I found two persons? And Bob said, oh, Chin-Yih, you are right. Those two specimens were from the same person at two different time points.
Wow.
And so I was very happy to see that. But then this is the time that Florida dental study came about. So in the laboratory, actually, we were testing the idea. And so when Jim Kern, the director then, mentioned to us that there was such a case, and I thought, easy enough. We know how to solve this problem. And I thought naively that we should be able to solve it in 2 weeks, because we thought if there's no connection, then I can prove there's no connection, and that's done.
So going back on the, just one question for you. So when we say that the virus from the index patient, the person we know, and a contact, let's say, the similarity wouldn't be 100%. It would be a percentage of similarity. Is that right?
It cannot be 100%. Even in a single person, there will be different viruses. They're siblings all together, quasi-species. So move to another person, it cannot be 100%. If it's 100% identical, they will mean that actually you got a contamination somewhere. Or these two viruses are, from the same culture or something like that,
So just to recap, the Florida so-called dental investigation, again, this was 1990, and the Florida Health Department reported through their AIDS surveillance a young woman of about 21 who had AIDS, and she did not have any of the standard risk factors upon their studying her, but they identified the fact that she had had a dental procedure 2 years before her AIDS diagnosis. And it was found that the dentist had AIDS. So then additional HIV-infected patients of the dentist came forward, and they sent you the index patient and the dentist's specimens to see whether they were the same strain. So if you hadn't been studying genetic diversity, what would be the state of the art in terms of trying to link those specimens?
I couldn't think of one.
Okay.
Right, in terms of laboratory methods.
Right.
Right.
So were others using this methodology, or was this an early use of the methodology?
I think this is the early usage of it. And in terms of HIV, certainly the very first case I know of.
Okay.
Yes.
Can you tell us a little bit more about what your approach was and how it turned out for you when you were looking at these?
Like I said in the beginning, I had an assumption that they may not be a direct linkage, but we have to prove it to show that the two sequences from these two persons are not the same. I mean, they diverge.
Why was that your hypothesis? Just because yours and others?
Actually, I really don't know.
Yeah.
And my impression was that, she might got it from somewhere else, But I didn't really know.
Okay. But it hadn't been shown that this was a method of transmitting the virus.
Right. But genetic approach, DNA sequencing is the way to go. That's the way I look at it. And certainly, I was completely surprised. I shouldn't have said that because I really don't know what to expect. But I was surprised to see that they are so close. They are not identical, but they are close, very similar.
So how long did it take you to do this? There must have been a tremendous amount of pressure on you at that point.
At that point, actually, I didn't know exactly what to expect. So I didn't really have, in the beginning, I have to admit, I didn't have that kind of pressure that I felt. And because we done some of the work already, groundwork already, and it was very natural. We said, okay, we got this case, interesting, and we had to do it the way that can be best done in the world. And like I say, contamination can be a problem, that we have to do things right, and we receive the specimens from Carol Shosaki, who did the groundwork, and I think I was trying to be very careful to make sure that if something happens, there will be a legal problem. So right from the beginning, I would segregate the work. We have two PhD staff in our section taking care of one person and specimen, and the other one take care of the other one. And they are in two different floors. So if this lady's sample, you do it up there. For the dentist, you do it down here. You two do not walk into each other's room at all, and that kind of thing to segregate the work. And later on, when sample gets more, from other patients, as well as the local controls, because we had to build in local controls, the specimen don't even come into our laboratory. We have Charles Shaber, who is in charge of serology laboratory, would take care of the work for me, so that people will not say, oh, Chin-Yih contaminated the sample,
Wow.
So it will be somebody else handle the specimen, and I will ask Charles, today we need the specimen, and he will request for me, and so this custodial type of chain was very clear-cut right from the beginning. And that helps CDC's reputation later on. And certainly at the end, Harold Jeffy also decided that some of the specimen would be sent over to Scotland to retest.
Now, Scotland, was that another lab that was
Yes.
proficient in doing this?
Well, that's what I thought, but it turned out to be the right choice. And actually, I don't know them much at all, but people recommended that this would be the
In
right.
terms of doing DNA sequencing, or did they actually have experience and expertise in HIV DNA?
Oh, they have, but later on, this story was written by the GA, the government accounting office person, Mark Ron, and reading the article, that book, I realized that actually the Scottish laboratory failed to amplify DNA in their first trial, and then they have to modify their methods, and later on they got the result.
Oh.
But at that point, interesting to talk about this. To me, I was under heavy pressure. I did my best to make sure the laboratory operations correct. Things got segregated, got different people doing several things. We checked the HLA of the patient specimens to make sure they belong to two different HLA types. Meaning there's no missing of specimens and that kind of thing. And some of the samples, we have multiple samples, we double check. And I knew our operation is clean, nice, and perfect. Mm-hmm. But what happened if this laboratory, which is supposed to verify our results, did something wrong, Mm-hmm. You see what I'm saying? And so when the result came back and received the fast result, I sat there for 5 minutes. I don't know what to do. I want to make sure that the result is the same as ours. And I checked one nucleotide after another. And I was so happy when I saw the result identical. I called up Harold and Jerry that they duplicated our results. They verified our results. Yeah.
So this had, of course, huge implications from a policy point of view,
Sure.
that it would be possible to acquire HIV in a dentist, even though from an infection control assessment, they were never able to really confirm a method
True.
of transmission.
True.
There were a variety of procedures that
Yeah.
could have likely punctured and so on.
Yes.
So
even these days, I went to see my dentist. I was opening my mouth there, and every time I would think about this thing, and regardless, the dental operation here in this country becomes much better, cleaner, and things like that. And I also had seen my dentist in other places, and I always wonder, has this been done correctly in terms of your operation? Keep your place clean or what?
So you were really at the center of so many intense outbreaks and methodologies for diagnosis. Did you feel a part of? Did you have a sense of being a part of a team? What was the? We see lab and we see epidemiology, the programmatic people, or the ones that are doing operational research, and then the lab is somewhat separate at CDC, but it sounds like you were really in the mix. Can you comment on that at all?
I think this is really a great thing about CDC, and certainly I was lucky. I moved into this lab epi collaboration and produced wonderful results, and many of them influenced the national policy, and so I was very lucky. I'm not quite sure whether other places in CDC they are like that. Some of them may take a longer time, but because of PCR, that brings me to work with epi people just right away, and not just infant diagnosis, Martha Rogers' work, Bob Hosberg's work. Also, there works with hospital infections like Janine Jason, Bruce Everett, to look at the HIV in people with hemophiliacs, as well as some other studies. And later on, with Bruce Wellinger in Thailand, to look at the HIV diversity in a bigger situation in the country, as well as in many other countries.
Do you want to tell us a little bit more about the work with Bruce Wellinger and who was director of the CDC Thai field office during the early 90s in Bangkok?
Yes. That was a really beautiful study. And actually, I remember I went to Bangkok for the first time, probably in 1990. I cannot recall exactly when, and saw Bruce Wellinger there the very first time. And the next thing I realized that he said, "Hey, I have these specimens they collected from different parts of Thailand, and they were from person infected with HIV through IV drug use or through sexual contacts. Can you take a look at them?" And that study was fantastic. I was also completely surprised when the first set of results came out. And as I said, they were done also by Claudio Bendu, one of the PhD staff, and the other side from Chin-Yih Ou from the other side. They both involved in our Florida dental studies. I think I forgot to mention their name. I'm sorry for that. And also at that point, I also got new people like Marsha Kalish, who was very helpful to me. And at that point, actually, we were also working on sequencing a lot of HIV from different parts of the world, like Haiti and in some African countries. And that was an NIH project that we helped work on.
Can I just ask you, what was the importance of that?
That actually, it's actually turned out to be interesting as well. With that particular study, we certainly submit our HIV sequences from different countries to Los Alamos National HIV database. And Jerry Myers, who helped us to determine the HIV Florida dental cases, was the director over there. And he told me that at one point, actually, the data from CDC, from us, contributes to his database quite a big chunk. And from there, also include other people's sequences, that he was able to find that there are different HIV clades or subtypes, HIV-1 subtypes, around the world. And so this is a new concept. You see different HIV-1 subtype clades in different countries. In some countries, they may be having 2 or 3. Like United States, beginning was infected with subtype B. And in Thailand, while we were looking at them, we found that actually in Thailand, there are 2 viruses in 2 different populations. They're basically segregated. And epidemiologically, this is completely a new concept. So when we find something like this, we say, what? What is this? When I first saw the data coming from those 2 groups from my shop, I said, we must be wrong. Let's go back and do everything over again.
So these 2 groups in Thailand, one was the IV drug using
Yes.
population, and the rise of HIV in Bangkok, as I recall, was dramatic. In early 80s, there wasn't much, and then late 80s, it started to just shoot up.
Shoots up, yeah.
In both the IV drug using population and the heterosexual, homosexual cases. So you had specimens both from the IV drug using and then from, was it heterosexual or STD clinics? Or yeah.
Yeah. And it's nice. It's just interesting to see them with 2 different viruses. One now is called subtype E and the other one subtype B. But at that point, there wasn't an E subtype yet, and so we called them, subtype. We call it A and the B,
So that helped trace the origin of the
Yes.
virus.
And
In other words, one might have thought that it was the same virus communicated through female sex workers or other ways that the populations interacted. What were the implications of this? We don't hear too much about it now. I guess there's emphasis on treatment, but what was your sense of the importance
at
of
that
it?
point, probably we can imagine that one virus is more transmissible than the other. It might replicate faster or something like that. And I don't know whether that turned out to be true, though. But that was a logical first reaction to this kind of distribution. And then you might then think, oh, maybe for vaccine preparation, you need to designate this vaccine for this particular population or the other population.
Right.
But it wasn't that way.
Right.
Yeah.
So just looking over CDC's laboratory strategy and emphasis, do you want to share some of your thoughts on what CDC focused on for the lab? And did you think we got it right? Or could we have done it better? It's certainly worked out well for your particular area.
True. There are quite a lot of resources in terms of financial support as well as technical people support for our HIV laboratory operation. And in CDC, my career in CDC, I did notice that in other areas they may not be like us. So I was fortunate to be in such a special unit that they will allow us, to do more, and hopefully, it will be the same for other area as well. But I would think, as you alluded to, that the close collaboration between the lab people and the epi people are essential. I was in a particular situation that I moved into it quickly, and because the leadership, both from our laboratory part and also from the epi part, Harold Jeffy, as well as Jim Curran, they are so supportive. And one thing I might want to add is, I'm from an Oriental culture. I kind of see things a little bit differently from people like you. And I was surprised, actually. I told my wife during the Florida dental investigation, there are times I went home and I see the national news. And I was so stressed for them. And I look at it and I say, what happened if I miss something? And then I would screw up the reputation of the entire organization here. And yet, I told my wife that I never hear a doubt from Jerry Schuckerman, from Harold Jeffy, or from Jim Curran. They never ask me, hey, Chin-Yih, are you right? They never say anything like that. And so in this case, I was completely grateful. And in the Oriental culture, my boss would say, hey, did you screw up? They would say that. So in this case, I was very appreciative that I'm lucky enough. I'm working here in this organization. They gave me the complete trust and give me everything I need to get the work done. And I can never forget them my whole life.
You worked on AIDS a big chunk of your career, later on working for PEPFAR, the President's Emergency Plan. Did you ever worry about getting AIDS?
Never. I never think, that I would get AIDS. And I basically, I believe whatever word that CDC put out there, because we told people, you don't get AIDS by sitting in the toilet, you don't get AIDS through just a little bit kissing or that kind of thing. No, I never afraid that I would get HIV at all.
Was there concern early on among laboratory staff?
And certainly, yes. If you are working in the HIV culture laboratories, that they may have a high concentration of viruses. Mm-hmm. Yes, they are concerned. And you know that there are incidents like that before, especially in monkey virus, So there was a concern. Mm-hmm. But personally, I never had a concern. Mm-hmm. And I'm happy working, all my life. 28 years in CDC. With the exception in the middle, 6 years, yes, more than 20 years in CDC. I never have any doubt at all.
Thank you so much.
Appreciate it.